When mission controllers predict a satellite's path years into the future with just incredible accuracy, you might wonder, how do they do that? Well, it's not magic. It's all built on a handful of powerful, elegant equations. Today, we're going to dive deep into that mathematical bedrock of astrodynamics, the fundamental principles that govern literally everything that moves in space. And to set the stage, let's start with this amazing quote from the one and only Carl Friedrich Gauss. He was talking about trying to figure out the orbits of the very first asteroids. It was a problem so tough that even a mind like his felt led astray. It just perfectly captures this huge intellectual puzzle that has fascinated scientists and engineers for hundreds of years. All right, so where do we even begin? The entire field of what we call two-body orbital mechanics, all of it, is built on one single powerful physical law. And that law is, of course, Newton's law of universal gravitation. Now, to make the math clean, we have to make a few simplifying assumptions. We're going to treat our planet and satellite like perfect point masses, and we'll assume gravity is the only thing going on. The law tells us that our big planet M and our little satellite M are pulling on each other with an equal and opposite force. That's why these equations look so similar, just with the sign flipped. They're vectors pulling these two bodies straight towards each other. Okay, but trying to track both of these objects moving through space at the same time, that's a huge headache. So engineers came up with this brilliant simplification. We're going to describe the motion of the satellite relative to the main planet. In effect, we just nail our coordinate system to the center of the big body. And just like that, a really complex two-body problem turns into a much, much simpler one-body problem. And this is what you get. This beautiful thing right here is the two-body equation of motion. This is, and I'm not exaggerating, the master equation of astrodynamics. That R with two dots over it, that's just the acceleration of the satellite relative to the planet. And that Greek letter mu, that's the gravitational parameter. It's just a handy constant that lumps the masses of the two bodies and the universal gravitational constant all together into one number. This one equation tells the whole story. So we have this incredibly powerful equation, but what does a solution to it actually look like? I mean, what kind of paths can an object in orbit actually follow? And the answer is just so cool. It's one of the most elegant results in all of physics. The only possible solutions are the conic sections. That's it. An object in orbit has to follow one of these four paths: a circle, an ellipse, a parabola, or a hyperbola. There are no other options. It's this perfect, beautiful marriage of mathematics and the physical world. So how does a satellite choose its path? What makes it an ellipse and not, say, a hyperbola? Well, it all boils down to two key numbers. First is its specific mechanical energy, which is basically its kinetic and potential energy all rolled into one. Second is its eccentricity, E, which is just a number that tells you how stretched out the orbit is. And as you can see here, if you've got negative energy, you're stuck. You're in a closed, bound orbit, a circle or an ellipse. But if your energy is zero or positive, whoosh, you're on an escape trajectory heading out of the system on a parabola or a hyperbola. Knowing the shape is a great start. But if you're actually trying to, fly a spacecraft, you need more than that. You need to know its size, its shape, and its exact orientation in three-dimensional space. And to do that, we use a very specific set of parameters. And here they are, the 6 classical orbital elements. Think of these as the 6 coordinates you need to give any orbit a unique address in the universe. The first two we've already met: semi-major axis, A, for size, and eccentricity, E, for shape. The next 3, inclination, longitude of the ascending node, and argument of periapsis, are all angles that pin down the orbit's orientation in 3D space. And the last one, the true anomaly, tells you exactly where the satellite is along that path at a specific moment. Together, these 6 numbers give you a complete, intuitive picture of the orbit. Okay, so far we've kind of been cheating. We've assumed we already know these orbital elements. But what about that inverse problem, the one Gauss was wrestling with? What happens when you spot a new object in the sky and you have to figure out its orbit completely from scratch? This right here is the fundamental challenge of orbit determination. How do you go from just a few observations, a couple of blips on a radar screen, a handful of telescope sightings, and turn that into a complete set of those 6 orbital elements we just talked about? Well, here's the amazing thing about the classical method. You don't need tons and tons of data. You just need 3 good position measurements. That's it. From those 3 points in space, you can use some pretty clever vector algebra. You calculate these intermediate vectors, d and n, and then you can solve for key parameters like p and the eccentricity vector e. And once you have those, boom, you have everything you need to define the orbit's geometry. Now, it's really important to take a step back here. Everything we've built up so far is based on this perfect, clean, two-body system. But as you know, the real universe, it's a lot messier than that. Just take a look at the numbers for a satellite in low Earth orbit. Earth's gravity is the big boss, no question. But look closer. You've got these tiny little gravitational tugs from the moon, the sun, even from Jupiter way out there. We call these perturbations. And yeah, they're tiny, but they are constant. They never stop. And over weeks, months, and years, they absolutely add up and pull the satellite off that perfect path we calculated. So how on earth do you handle that mess? Well, engineers have this really elegant concept called the oscillating orbit. Oscillating actually comes from the Latin word for to kiss, and that's a perfect description. At any single instant, we can define the perfect two-body orbit that is instantaneously kissing the satellite's real messy trajectory. Then, a moment later, we calculate a new one. By constantly updating this oscillating orbit, we can accurately model the true perturbed path through space. So the two-body solution is this incredibly powerful and elegant idealization. It gets us, let's say, 99% of the way there. But to truly master astrodynamics, you have to account for those real-world perturbations. And that leaves us with one big question to chew on. What new mathematics do you need to master that true perturbed motion? The answer to that lies in the advanced field of perturbation theory. But that, my friends, is a topic for another explainer.